Hello students and welcome to the new lecture about solutions. Solutions are defined as homogeneous mixtures of two or more substances. They are made of two major components: the solute, which is the substance present in smaller amount, and the solvent, which is the substance present in the larger amount. There are so many examples of solutions. So here is one common, which is your soft drink. The solvent is water. However, the solute, we can have multiple solutes, can be sugar, carbon dioxide, dyes, flavors. Like there are so many molecules that actually are solutes in your soft drink. Air and also gas can be a solution. Gas state can be a solution. The solvent is whatever exists in the larger amount, and in air that will be nitrogen gas. And the solutes are the substances exist in smaller amounts, and in that case it will be oxygen, argon, methane, water vapor, etc. Solution stoichiometry and concentration. In order to understand stoichiometry for solution, we have first to understand concentration. In a solution, concentration is a measurement that tells me about the amount of solute in a given quantity of solvent or solution. The most common concentration unit we use is molarity, and it is calculated by dividing the mole of the solute by the volume of the solution in liter. So the volume has to be presented in liter. Let's look at this example together. What is the molarity of a solution containing 232 grams of potassium iodide in 500 milliliter of solution? So remember, molarity is the moles of the solute. For the solute here, we actually were given grams. So I'm going to start with 232 grams of potassium iodide. And I'm going to convert that into mole because I need the moles of the solute. So I'm going to say for 1 mole of potassium iodide, the molar mass will be 166.0 grams of potassium iodide. So now grams of potassium iodide cancels out. I have 1 mole of solute. What I need to do is to divide that by the volume of the solution. Did they give me the volume of the solution? Yes, 1/500 milliliter, and because I can convert milliliter directly to liter, I can say times 10 to the negative 3 liter of solution. And I put 1 over because I need to divide by the volume, okay? So if this is here, what's left, guys, I'm going to highlight it. So if you look at what's left here in your equation, the moles of the potassium iodide, when you look at the units that didn't cancel, over the liters of solution. So that should give you the molarity. You should keep 3 sig fig. The answer will be 2.7. Actually, when you going to round, 2.80 molar. This is the concentration unit, molar of potassium iodide solution. Okay, so big M. Remember, big M is molarity. All right, let's look at the next slide. What is the molarity of a 50 milliliter ethanol solution containing 1.3 grams of ethanol? So this is here, again, similar example. So I will keep this for you to practice home. I will show you the setup and you guys going to continue. So again, remember, molarity is moles of solute over liter of solution. Your solute here is ethanol. So you're going to start with 1.36 grams of, I'm going to abbreviate ethanol. This is here the organic chemistry abbreviation of ethanol. And then what you need to do, convert that moles of ethanol. And then here you're going to have the molar mass of ethanol. And then you're going to have here 1 over volume of solution, which is given to you here. However, it has to be in liter. So please do the work and figure out the molarity of the ethanol solution. This is one practice for you. Using molarity as a conversion factor. This is a very, very important topic. Now I'm going to show you something. Molarity is moles of solute divided by liter of solution. So it is a relationship between the moles and the volume. And therefore, when I can express it in a way that if I have molarity and volume, I can get moles. If I have moles and molarity, I can get volume, and so on. So remember this when you are given, for example, if somebody told you the hydrochloric acid solution in the lab has a molarity of 1.50 molar. Now this is here considered a fact, and because it's a fact, it's an equity, and you can write two conversion factors. So what does that mean here? It means that there is 1.50 mole of HCl for every liter of HCl solution, right? In every 1 liter of a solution, there is 1.50 mole of HCl. So anytime, I also can say a liter of HCl solution has 1.50 mole of the solute, which is hydrogen chloride. So as you can see, I can use two conversion factors. Every time I have a molarity, I can use the molarity as a conversion factor that states a relationship between moles of solute and volume of solution in liter. So let's look at this question. What mass of potassium iodide is required to make 250 milliliter of a 1.53 molar potassium iodide solution? All right. What I want you to figure out here is what you have. This here is volume of solution. And this here is a concentration of a solution. It's in molarity. So what I need you to do is immediately write what does that mean to you as a relationship. It means there is a 1.53 moles of potassium iodide for every liter of potassium iodide solution. Now, they want the mass of potassium iodide. But what did they give you? They gave you volume and they gave you molarity. Molarity has a relationship between volume and moles. So I have volume and I have molarity. It means that volume can cancel volume and I will get moles of potassium iodide. And if I have moles of potassium iodide, I can get grams of potassium iodide. So let's start working on this together. If I have 250 milliliter of potassium iodide solution, I'm going to use the molarity conversion factor to take that into moles. I will say there are 1.53 moles of potassium iodide for every liter, or I can make my life easy and I say for every 1000 milliliters, so I can immediately cancel with the milliliter. of potassium iodide solution. This came from the fact that every liter is equal 1000 milliliter. Now last part is to take, see now milliliter cancel out. I have moles of potassium iodide. I can take that into grams. I can say there are 166.0 grams of potassium iodide for every 1 mole of potassium iodide. When I do the math, I need to keep my 3 sig fig. The answer will be 63.5 grams of potassium iodide are required to make that solution. All good? Now we are going to look at the next question. What volume of hydrochloric acid solution is required to make a 3.75 molar hydrochloric acid solution that contains 34.2 grams of hydrogen chloride? Let's see what they gave us. They gave us mass. This is mass of solute. But they also gave me molarity. And molarity, remember, what does that mean? There are 3.75 moles of HCl in every liter of HCl solution. Now, they want volume. However, mass can be converted to moles. And if I have moles, the moles can cancel out with the moles in the concentration, and this will lead me to have volume. Let's look at how we're going to do that. Now, I'm going to start with 34.2 grams of HCl, and I'm going to convert that into moles. So I'm going to say 1 mole of HCl has a molar mass of 36.46 grams of HCl. Now grams cancel out and I have moles of the solute. Now I'm going to use the molarity conversion factor, and I'm going to say, okay, here is what I know. I want to cancel moles of HCl. So I'm going to say for every liter of HCl solution, or 1000 milliliter, both will work. Since they didn't really specify the unit in which they want the volume, either one will be good. For every liter of HCl solution, I have 3.75 mole of the solute. So now this will cancel out, and I am left with liters of solution, and I have to keep 3 sig fig. The answer will be 0.250 liter of HCl solution. So the point here of these two questions is to use you that molarity is used as a conversion factor that can take volume of solution to moles of solute, or moles of solute to volume of solution. How to prepare a 1 molar solution of copper 2 nitrate? First, it is easy to remind ourselves the definition of molarity. 1 molar means, 1 molar solution means 1 mole of solute in a liter of solution, right? So our solute here is copper 2 nitrate. So 1 mole is really the molar mass of copper 2 nitrate. I definitely can calculate that, and I can weigh it. After I weigh it, I can transfer it to a volumetric flask that has a total volume of 1 liter. I keep adding water till the volume of the solution, not only not the solvent, the volume of the solution, meaning the volume of the solute plus the solvent together equal liter, which is what the volumetric flask line here will be. I will swirl, and then that is a 1 molar. So if I am looking at the steps here, you add the 1 mole, which is the 187.5 gram, it's the molar mass of cupric nitrate, to 1 liter volumetric flask. You mix and you fill water to the line, so you make sure that the final volume of the solution, meaning solute and solvent together, is equal to 1 liter. Next, we're going to look at dilution. Dilution means prepare a less concentrated solution from a more concentrated one. Here is an example. If I have a very salty solution here, what I'm going to do to make it less salty, I'm going to add more water. All I did, I increased the amount of solvent. However, the amount of solute is the same. That is dilution. What would the dilution do? It will affect the concentration, but the amount of solute was not affected. Meaning, if I had 5 grams of salt before, I still have 5 grams of salt after. Right? Which means moles of salt before equals moles of salt after. The only thing that did change is the volume of the solution, because I added more solvent, which will affect the concentration because the concentration is dependent on the volume. So moles of solute before dilution, as I said, are equal to moles of solute after dilution. And this is where the dilution equation comes from. M1V1 equals M2V2. So let me show you and prove to you that this is correct. Molarity is mole of solute over volume. That is molarity. If I multiply molarity by volume, then volume cancel volume, and I'm ending with mole of solute. Same thing here, mole of solute over volume times volume. So I end up having mole of solute before equals mole of solute after. V2 is the total volume of the solution after mixing. So V2 here is the final volume after adding more solvent. Okay? How would you prepare 60 milliliter of 0.2 molar nitric acid from a stock solution of 4 molar nitric acid? Then approximately how much water would you need to add? This is a very good question, and a very important thing is to immediately recognize that this question is a dilution question. What is your key for that? It is the same substance. It was less concentrated one time and more concentrated the other time, meaning what you have here is nitric acid, right? This is a smaller concentration, this is a larger concentration. The moment I recognize that I have that, then what I do is try to label what is M1, what is M2, what is V1, and what is V2. How would you prepare 60 milliliter of a 0.2 molar? Starting from a stock solution that is 4 molar. Okay? Now, this is your final volume. This is V2. That's what you want to prepare. 0.2 is your final molarity, which is normally the lower concentration. Here is the lower. Let me erase this. This is here is the lower concentration. This is here is the higher concentration, which means this is normally is the small volume, and this here is the large volume. Okay, so this here is M2, and this high concentration has to be M1, which means I am solving for V1. V1 is the volume you needed to initially have from the stock solution. So you go to the stock solution and you take 4 ml. So now we go M1 V1 equals M2 V2. Clearly we are solving for V1. So V1 equals M2 V2 over M1. Now let's put our units. M2 was 0.200 molar. V2 was 60 milliliter, and you can keep it in milliliter, and I will show you why. Then M1 is 4 molar. The reason why you keep it in milliliter, because molar cancels molar. And what does that mean? That the final volume is gonna come in milliliter. So if you do this simple math here, the volume will be, and you're gonna have to have sorry, just keep my sig fig straight. You're going to have 3 sig fig, so 3.00 milliliter stock solution. So you go to the lab and you're gonna take 3 milliliter from that high concentration. Are you done? Did you really prepare what they wanted? No. What are you gonna do to the 3 ml? You're gonna say, I will add 57 milliliter water. At the end, if I do that, I will have 60 milliliter of 0.200 molar, right? Where is the 57 coming from? It is 60, which is V2, minus 3, which is V1. So this is V2 and this is V1. This is the amount that you need to add solvent added, right? That is the volume, sorry, that is the volume that was added, which is the final volume minus the initial volume of your higher concentration solution. Here is another question. 34.2 milliliter of 5.07 molar sodium hydroxide is mixed with 165.8 milliliter of water. What is the final concentration? Okay, let's see what we have. 34.2 of the higher concentration is mixed with water. So what does that mean? That is V1 and that is M1. Is mixed with that amount of water, right? This is not V2. However, I can calculate V2. V2 will be 34.2 milliliter plus the amount of water added, which is 165.8. If you add this together, you're going to have 200.0 milliliter. So now I can calculate the final concentration, which will be the diluted concentration M2. So what we say is M1 V1 equals M2 V2. I am solving for M2, which is M1 V1 over V2, and the answer here, M1 is 5.07 molar times volume 1, which is 34.2 milliliter, and you will see why I can keep it milliliter, because V2 is 200 milliliter. So milliliter cancel milliliter, and I'm going to get my answer out in molarity, 5.07 times 34.2 divided by 200, and I'm going to keep 3 sig fig. The answer will be 0.867 molar. All good? Now let's look at solution stoichiometry, and I'm going to bring this to your attention again. Solution stoichiometry, how do you identify it from dilution? M1V1 equals M2V2, that is only a dilution equation. It's not solution stoichiometry. So the students will ask me, how do I know it's a solution stoichiometry? I'll tell you, it's very simple. You will have two solutions that are not the same. Let's read this question. What is the concentration of the sodium hydroxide solution if 150 ml of the sodium hydroxide solution is required to titrate, which means completely react, with 200 milliliter of sulfuric acid, which has a 4.5 molar. So how do I know they are solution? Because they have molarity, right? And volume. So this is acid and this is base. I'm not like diluting the same concentration like in the previous example. These are two different concentrations. This is a reaction. And because it's a reaction, I'm going to have to write my balanced equation. So I'm going to have sodium hydroxide solution reacts with sulfuric acid solution to give sodium sulfate aqueous, which is the salt, and water. Now you will have a quick look at this and you will understand it's not balanced, so you have to balance it out. Now what I do next, which is really important, I'm going to write the equation again, but what I want to show you here is I want to identify what do I have for every substance in this equation. So if you look here with me, guys, you will see that for the base I have volume, and for the acid I have volume and molarity. Okay, so let's write the equation again. 2 sodium hydroxide reacts with sulfuric acid solution to give me sodium sulfate solution and 2 water. Now what we will do, we will start with understanding what do we have. Now look at this equation. It's a balanced equation. For this here, remember in stoichiometry we always go to the mole. Look at this picture. What's in the middle? What's the core? Those blue blocks are the mole. If I have a mole about one substance, then I can get the mole about the other substance, and I can get information. If I have mole and I have molarity, I can get volume. If I have moles and I have molar mass, I can get grams. Same for A. So here's what I found. For the base, I only have the volume. But for the acid, I have volume and I have molarity. In stoichiometry, the rule is always go to moles. Which substance of these two has enough information to give me moles? It's the acid, because as I showed you before, if you multiply molarity by volume, molarity is mole over volume. If you multiply this by volume, you get mole. So for the acid, I have volume and I have molarity, so I start with the acid. What do I know about the acid? I know that I have 25 milliliter of the acid solution, and I know the molarity. The molarity is there are 4.50 mole of H2SO4 for every 1000 milliliter. Instead of a liter, 1000 milliliter, so I can cancel liter of the sulfuric acid solution. Now this cancels this, and I have moles of the hydrogen sulfate. Now I can convert that to moles of sodium hydroxide by using the mole to mole ratio, because that's stoichiometry. So I will say 2 moles of sodium hydroxide are needed for every 1 mole of H2SO4. Now these cancel out. Now that I have moles of sodium hydroxide, they want molarity. Molarity is dividing moles over volume, and that volume has to be in liter for molarity. So I'm going to say 1 over 158 times 10 to the negative 3 liter, because it's molarity now I want to calculate, of sodium hydroxide solution. I'm going to keep 3 sig fig, and when I do this math, the answer will be 1.42 molar of sodium hydroxide solution. That was the concentration of sodium hydroxide. Actually, I'm going to do this, write the answer up again. It's 1.42 molar of sodium hydroxide solution. Okay, so now let's see one more question. How many milliliter of a 6.2 molar sulfuric acid solution are needed to neutralize 30.4 milliliter of 0.256 molar potassium hydroxide solution? So now again, is that a dilution question or is that stoichiometry? And you know the answer by thinking, okay, is it the same solution that I have 2 different concentration or 2 different substances? The answer, they are 2 different substances reacting. So the first thing you need to do is to write the reaction down. You have 2 molar of potassium hydroxide solution balancing, reacting with sulfuric acid solution to give you potassium sulfate solution and water. Now, let's do what we did before. Go to your equation. What do you know about the base? There is the volume and then there is molarity. So I have volume and I have molarity. What do I know about the acid? Only molarity. So I always go to mole because it's a stoichiometry. The base is what's going to give me moles. So I start with the base. There are 30.4 milliliter potassium hydroxide solution. I multiply that by molarity, which is 0.0256 molar of mole of potassium hydroxide in every 1000 milliliter of potassium hydroxide solution. Now milliliter cancel milliliter, I have moles of potassium hydroxide. Let's convert that into moles of sulfuric acid. 1 mole from my balanced equation of H2SO4 is needed to react with 2 moles of potassium hydroxide. finally, what they want here is the volume. They gave me molarity, so what I would say, there is 1,000 or 1 liter, it doesn't matter. Oh, actually they want milliliter, so it does matter. 1,000 milliliter of sulfuric acid solution for every 6.2 moles of H2SO4. That came from the molarity. You do the math and you keep it 3 sig fig, so let's do the math together. 30.4 times 0.256 divided by 1,000 divided by 2 multiply by 1,000 and divided by 6.2, which is 2 sig fig. So my answer has to be in 2 sig fig, and the answer will be 0.63 molar. 0.63 milliliter of H2SO4 solution. Okay, that does conclude this lecture. I hope you enjoyed it, and I will see you in the next chapter. Take care.